privilege to be here today. Just to start off here, out of curiosity, how many of you folks currently either employ directly GPU technology on the server side or seriously thinking about it? Oh, quite a few of you. That's really interesting because absolutely nobody in Raleigh was at that point. So consider yourselves vastly superior already. Good work, folks. Good work, folks. Okay, well, the nice thing about GPUs is that they do a lot of wonderful things for us. And so, first of all, it always begs the initial question, well, why do you even want a GPU in the first place? So I'm going to start by showing this graph, which very dramatically illustrates how Moore's law over the last few years is failing fairly miserably. Moore's law, as you recall, is essentially doubling the CPU speed, 1.5 times the CPU speed on an annual basis. As you can see, this curve has already started to bend over as of a few years ago. And in contrast to that, if you look at the direction where GPUs are going, I mean, we're talking, as it says, something like 1,000 times of improvement in the performance by 2025. And with any luck, I'll be long retired by then, but a lot of you folks are going to be able to reap some incredible benefits of that technology. Point being that investing in CPU technology effectively does not gain you nearly as much as it used to over the past decade. And if getting the most bang for your buck, so to say, out of your systems is important, and you want to do that with a cost-effective means, this is definitely a technology to seriously take into consideration. Okay. Well, clearly, when you offload tasks from your CPU onto some kind of an accelerated processor, many of you will remember that coprocessors were very, very popular early on for taking, in particular, things like arithmetic functions and separating them out from the CPU in order to be able to perform the math a lot quicker. This takes it to yet another level. And so, if you imagine, for example, even if you can save 10% of your CPU load, and you have to buy 10 servers, well, you've already saved the cost of an entire server in the process, which is not unsubstantial. And depending on, of course, the type of GPU that you put into the system, at some point this is going to become very potentially a cost-effective solution. Parallel processing, of course, is another really interesting thing. I'll talk a little bit later about the fact that contemporary GPUs now not only have the capabilities of accelerating graphics, but in addition, when they're not being used for such purposes, they can be repurposed to run computational tasks with things like TensorFlow and CUGC and such. You have the ability to do things like artificial intelligence, machine learning, and deep learning.
Bitcoins.
The ability to repurpose these devices, and not even really repurpose, but to factor in the ability to use them for an entirely different purpose is, of course, an enormous benefit. As I just mentioned, compute mode, in some cases, can be now switched on the fly. It used to be some of the older modules that you had to sort of go through a rebooting kind of a process. But with some of these contemporary devices now, you literally issue a software command and bingo, you're already switched over one way or another. Application and graphics acceleration. Which applications do you folks think benefit from GPUs? All of them, exactly. It's not a trick question. The fact is that every single application runs better. Obviously, some applications are going to run better than others. And one of the key factors in considering the usage of GPUs is, especially if you have costs that you have to take into consideration, is weighing in, if you cannot accelerate everything through a GPU, at least take into consideration what particular applications are going to benefit the most from such a process. Here's one of my favorites. This is one of the primary reasons, in fact, that we got interested in this technology early on, namely that at my university, Northern Arizona University, we have a fair number of labs on campus, but as with many universities, costs and other constraints have caused us to scale back these to some degree. Well, what do you do then? A student needs to run ArcGIS or AutoCAD or Revit or something like that, but doesn't want to go trudging across campus when it's freezing or sub-freezing or at midnight. There are safety concerns, there are convenience concerns, and many thousands of our students don't even live on campus. So what are they supposed to do? Drive in and park or take the bus or whatever. Well, this is where ubiquitous computing becomes more and more important. And the ability to access applications kind of along the same line as what Citrix touts, being able to work from anywhere at any time, really has become a reality when you can provide these applications that are hosted on servers that are literally accessible from not only on campus but also off campus, and in fact from anywhere in principle in the world. And not only that, but pretty much with almost any imaginable device. Citrix Receiver, for example, or RDS-based programs really allow you to access ubiquitously pretty much any application that has a reasonably configured backend on it anytime from anywhere. Economies of scale and resource allocation. Well, here's another one. Why would I spend a lot of money to purchase very expensive high-end PCs or Macintoshes with very expensive graphic boards for possibly several $1,000s, and have them sit in somebody's office or have them sit in the lab where they sit idle probably easily 2/3 to 3/4 of the time. If instead, for the cost of just a few of such units, I can incorporate a graphics board that has similar capabilities and which can be leveraged by a very large fraction of the end user population, I'm going to get much higher degrees of usage out of it, and above all, I'm not going to restrict the usage of that device by any physical constraint. And so there's another very interesting benefit. HPCs. Supercomputing is becoming more and more interesting. 4 out of 5 of the world's fastest supercomputers now heavily leverage GPUs in order to achieve that. And not only do they attain incredible speeds, in the sense of petaflops and such, but also the power consumption typically has gone down significantly. And what that means is that a data center that has a high-performance computing center built into it can actually afford to grow because the amount of power needed to provide a certain amount of computational power now has dropped significantly. because of the greater efficiency that GPUs offer. What I want to show you is a video here, which is done by some folks that I know who work at a place called Rex Analytics. These are some real smart folks that are putting together some very interesting test and evaluation software. And what you'll see here, if I can get this thing started, is that on the left side, you'll see one instance where you are making use of a GPU, and on the right side is exactly the same thing, which is being performed purely by a CPU. I think the battery is dead. This happened yesterday, by the way. Same thing. But what you can see here is note that the CPU is running at maybe something like 10% only in the case where the GPU is leveraging most of the graphics rendering. Whereas on the right side, the CPU is basically pegged. The network obviously is going to be very, very similar. You're still pushing the same number of pixels across. But the fact that you can do better and faster, more frames per second, better rendering with probably a reduction of a factor of at least 4 in terms of the CPU load is pretty darn impressive. So imagine, any kind of an application that requires this kind of graphics acceleration. And then imagine any even kind of more mundane type of thing, like an Excel spreadsheet or a YouTube video. I mean, literally anything is going to profit immensely from this kind of thing. And as I mentioned before, obviously the degree with which it will profit is going to vary, obviously depending on the individual application. But in this particular case, where in particular you have very graphics-intensive types of operation, it does make an enormous difference. Okay. All right. Now that we've covered the basics, basically there are 3 primary vendors now that are in the GPU market: AMD, Intel, and NVIDIA. And all of these companies have to some degree both on-premises as well as cloud-based operations. We're going to focus mostly on the on-premises kind of possibilities these days, mainly just because that's where we're at right now. And also that area is evolving and changing very, very quickly, but I definitely wanted to touch on that. The other thing I wanted to mention briefly is that at the GTC conference, which actually just took place last week in Silicon Valley, NVIDIA brought out a whole new unit specifically that they said now is going to address this kind of interesting in-between area, which they dub data science. And that falls between the category of pure supercomputing and that of just general graphics types of acceleration and lower end types of computing problems. One of the demos that they gave involved doing basically almost real-time analysis on a spreadsheet that had 500 million rows of data, and they were able to accomplish that literally within seconds. Let's see if this is now going to work again.
I think you have to hold it in.
Good thing it's not karaoke. You probably wouldn't want to hear that. Point being that the GPU technology sector is not at a standstill point in time by any token of the imagination. CPU growth, very predictable, pretty static at this point. GPU technology, most definitely not. Okay, let's start with AMD. AMD has a wide variety of attest to some of his experiences with AMD. Not all of them, as you can see, specifically are supported, at least yet, in a Citrix-based environment. But there are a couple of different options, both in terms of cloud offerings as well as what you want to put in your data center. These are fairly typical configurations, and as you can see, typically the general card is designed so that you can deliver applications for up to 16 different virtual machines. We also have Intel who's in the game, the so-called Iris Pro series. Notice that in particular in the VP3 units that have been shipped now by Intel for quite some time, that there's actually a very small GPU component that is built into the CPU. And the cool thing there is that it is leveraged automatically by any application that happens to run within that CPU. Up to 7, I believe it is, individual processes. And every one of those automatically gets accelerated. Now, what you can imagine is that the real estate available on part of the die that comprises the CPU is of course going to be very, very small. And so obviously we're not going to get nearly that kind of performance as you would expect to get from a very large dedicated card. Most of these cards typically go in PCI 3 slot. They're usually X16 in format. And in some cases, you even require ancillary power to be delivered to the card in order to give it enough power to be able to run, since the PCI slot is not capable, in some cases by itself, to power the device. You don't need any special drivers in this case, which is really nice. There's no licensing involved. And what to me looks extremely interesting is that over the next year or so, Intel has announced that they're coming out with something called XE series. We know relatively little about it, but clearly riding on the coattails of probably the leading vendor in GPU technology these days, which is NVIDIA, they see enough of a market that they're very, very interested, of course, in cashing in on some of these things. So you might want to note that your URL there, it's great to see competition in the field. Everyone, in particular, I think the end user, is going to profit tremendously from this kind of competition. Then we have NVIDIA, and I'm sorry, everything's kind of crammed in here. NVIDIA blew me away when I was at Synergy, and I believe it was 2014, and introduced K1 at that time, and demonstrated what could be done in real time with graphics on the server. And as soon as I saw that, my thought was, wow, this is exactly what we need, because we have so many types of applications at my university that are very dependent on heavy graphics. And at that time in particular, we really didn't have that many workstations in any of our labs that had the capabilities of running these kinds of programs. And either they were sitting idle or folks were literally standing in line waiting to use them. And my thought was, well, if we can build up along these lines, we will have more flexibility and potentially even save quite a bit of money in the process. The M6 and the P6 on the right are blade-based. All the others basically go into a slotted server. Quite a few of them now have passive cooling, which is nice. You can see that the wattage ranges anywhere from roughly 300 down to as little as 70. The newest one of these actually is the T4, which uses the latest architecture. I'm going to talk a little bit about that chip in just a few minutes here. You can see that the nomenclature is the initial letter depicts the particular architecture that is used. So we have Volta, Pascal, Maxwell, and Turing, which is the newest one, the form of the T4. You can also see the virtual GPU profiles, that they can be chopped up into different pieces. And this is another very nice and somewhat unique feature of the NVIDIA GPUs, namely that you can take a portion of the graphics memory and in various ways dedicate it to be tied into a VM. So there are various scheduling needs that I'll talk about a little bit later if I have time, which allows you to figure out, well, do I want to dedicate this completely to a particular machine, or do I want to be floated around? How do I want to share the GPU cycles, which is really what it ultimately boils down to. And the idea of having dedicated memory, very similar to CPU memory, is that what you want to do, obviously, is you want to minimize the number of transactions that you have to do to swap in and out, because that's a relatively expensive process, right? And so if you can keep as much as possible contained within memory, you're obviously going to get a lot better efficiencies. Just briefly, a little bit about cloud options. Lots of different possibilities. Amazon Web Services, Alibaba, IBM Cloud, Google Cloud, Oracle. They've all got various configurations that you can get. Any number of those other chips that I mentioned on the previous slide are available to use, of course, on premises. The 100 series ones that were actually left are pretty much, if I recall correctly, dedicated mostly for, at least for use for computational needs. Some of the others vary in terms of, either more power or more density. The M10, for example, if I go back, is still actually the one that will provide the greatest user density in terms of the way that it can be chopped up into different pieces. Notice that it can have a profile as small as just a half of a gigabyte, which, believe it or not, for various purposes can be adequate. And the M10 actually contains 4 separate graphics engines. And the other thing that's interesting is that any of these GPUs that have multiple engines on board, you can take that individual engine and divide it up differently from another engine. So for example, one engine might have 1 gig profiles. The second engine might consist of, say, 2 gig profiles. And so you have that degree of flexibility. Now, if you have multiple physical GPUs, even if they only have 1 engine, course, configure each one of those completely differently. But it's important to remember that you cannot mix, for example, on the same engine within the GPU from NVIDIA. You cannot have, for example, both 1 gig and 4 gig profile on the same engine. One thing that NVIDIA provides, which is kind of unique, is what they call NVLink, which is just NVIDIA Link. This is supported within Zen Server, for example. And what it is a means by which if you have multiple GPUs within the same system, there's a special interconnect that allows them to talk to each other much more rapidly. And in addition to that, there's also a special means by which the GPU can talk to the CPU. So on the right side, you'll see, for example, the GPU engine, in this case, one of the Pascal engines, just as an example, has a very fast connect to its onboard high bandwidth memory module, up to a terabyte per second. And then you also have this very fast link that then goes to the CPU, which then in turn connects to the conventional memory on the CPU. One of the interesting features, in particular on the left side of the interlinks, is that NVIDIA, for example, will sell you a chassis like the GGX1, which has 8 physical GPUs that all have a very, very high-speed interconnect among them. And what that means is that you can run really, really big processes that transcend multiple GPUs, within that chassis. And if you imagine you're doing some data analysis or some machine learning on very, very large, complicated data sets, having that extra ability of being able to move the data around very, very rapidly is extremely important from a performance standpoint. Just a little bit about the T4, the very latest offering that just really came out, I guess, a couple of months ago. It was the T4. It's supported on Zen Server 7.6 and above. I've not seen a driver yet for Zen Server 8, which is theoretically supposed to be out before the end of this month. We'll see if that really happens or not. One of the very nice things, as you can see for yourselves, is that it's got some very nice built-in both decoding and encoding capabilities. It also has some very specialized registers that do not only CUDA core processing, but are also designed in particular to be optimized for the use in various machine learning and deep learning algorithms. And the little note on the left is kind of a reminder that one of the things that people forget about graphics is that unlike a typical TV type monitor that depends on 3 colors, RGB, right? Red, green, blue, that computers don't speak in that kind of language. They work in a whole different color encoding system. Partly because RGB is kind of slow and expensive and takes a lot of bits. And so what you do is you have various compression algorithms. One of the most common ones being YUV, where you have Y standing for luminance, which is basically the brightness. 0 is black, 1 is white, and then you have a certain scale, usually something like 256 levels in between. And then you have a U and a V, which is the so-called prominence, which is a balance between two color combinations. And you can see that there are a couple of different formats. There's a YUV444 and YUV422, of which, of course, the 444 gives you better coloration and more true colors. One of the cool things is you've maybe seen in some of the more recent Citrix releases with virtual apps and desktops that you can, for example, automatically detect where you have text, which in some cases requires actually a higher bit rate in order to form, especially very small characters, very accurately, whereas some of the images, for example, don't necessarily need that true of a coloration. And so being able to balance that is really, really important, because ultimately it's all about pushing pixels, right? And if you can cram more or less the same information into fewer data bits, you're going to get much better throughput, and you're also going to get a much better user experience. So anyway, I thought I'd throw that in on the side. It's kind of a side topic, but very interesting to me. I kind of come from a digital image processing background in astronomy. This kind of stuff becomes really, really important. And you think of satellite data and things like that too. Being able to transmit as much information as efficiently as possible also becomes extremely interesting and very important. Just a few specs on the T4 real quick. Instead of 8 gigs, it actually has 16 gigs of memory, which is essentially double. And in spite of that, it draws a maximum of only about 70 watts versus 75 watts. This just fits in a single wide X16 PCI slot. I don't have any yet. I'd love to have one. We do have actually quite a number of P4s. But just looking in the upper right there, you can see already, while the M60, which we also have a number of, the M60 and the P4 are kind of running neck and neck basically in performance, but the T4 really kind of takes off in terms of overall performance by comparison. Now that graph below, when I looked at it a little bit earlier, I was starting to think, well, wait a minute, how can this be 25 times as fast as the CPU if the CPU is rated at 5 and the T4 is rated at 25? So I asked NVIDIA if they could maybe explain that a little bit, and I hadn't heard back from that. So I'm not really sure exactly what's going on there. But needless to say, obviously there are enormous benefits compared to a pure CPU-based system. Now, briefly about licenses. NVIDIA licenses are horribly complicated, and I spent quite some time a couple of years ago arguing terribly with them about their licensing model when they came out with GUI 2.0, because originally for a virtual data workstation license, they wanted $6,000. I'm not kidding you. And there was a little bit of a revolution at the time, because they just came out of the blue and decided, okay, we're going to start charging people now. Well, it's become a lot more reasonable now, so to speak. It's still not that cheap, but again, here's the trade-off between how much do you actually spend eventually on hardware and how much do you spend on GPUs and GPU licensing. 3 basic licenses: perpetual concurrent licenses. You buy the license once, but in order to keep using it, you still do have to pay an annual subscription fee, which is of course significantly lower. The other is a subscription concurrent license, which is somewhat more expensive, but you pay a fixed amount on an annual basis. And for some of us lucky folks in education and nonprofit organizations, they also have an educational price program. And the details of that are a little bit hard to read, but you can see them here. This is all available online, of course. For virtual applications, $20 per concurrent user. Perpetual and $5 per year, or for the virtual PC license, $100, $25 a year, and for the virtual data center, $450 and $100 a year. Sums is support, updates, maintenance service, is what it stands for. The annual subscription price you can see below, and then the education price you can see at the very, very bottom. We get a really great deal, $99 a year for a virtual data center workstation license, which is a really great deal. One thing I should mention that's really complicated is that pretty much you have to think of the entire throughput, depending on your endpoint and your server point, everything has to match. So if you have a virtual workstation license, for example, running with, say, a cube profile, which incorporates that entire set also of quadro features, then any virtual machine that you have on the outside world that ties into that also has to have a virtual workstation license associated with it. On the other hand, if you run something like a 4A or QA profile, which does not incorporate the quadro features, then for any client to access those, you only need to have a virtual application license. And so you need to consider very carefully what applications need absolutely to have the quadro capabilities versus the ones that do not. I've run some tests with some of our highest intensity type of operations and found that there's a difference of roughly about a factor of 3 between a so-called 8 profile, which doesn't have the quad features, and the one that does. And in some cases, the frame rates drop to be so low that it's essentially unusable. And so before you make any kind of decision on what licenses you really need, it's really important to verify whether your particular applications are going to run sufficiently well, depending on which particular license level you take. And the other thing, of course, to take into consideration is what kind of profile do you assign, right? I mean, is 1 gig enough, or 2 gigs enough, or 4 gigs enough? It all depends. How many monitors does the end user have? What is the resolution of the typical image that they're going to be working on? Are they going to be using 4K displays, or are they going to use much smaller ones? All these factor in. Just in summary, for the support, we can see again that NVIDIA pretty much can do it all compared to the other vendors. Like I said earlier, I think competition is good, and I think they're going to continue to ramp up their development to at least try to catch up. Well, being kind of Citrix-centric in many ways, just wanted to show you real quick the 3 different ways that you can use, in particular actually, from different vendors, various configurations. If you do RDS, you have a 1-to-N mapping where you essentially can create a server and access that instance from multiple clients. It can be just basic desktops that run RDS sessions, or it could be clients that are just all connected to that same Zen app server as clients. You can also have a pass-through option, which is kind of similar in a way. One of the disadvantages of pass-through options is that you lose, by not having some of the more sophisticated profiles, the ability to do more specific monitoring of data usage and things like that. And then finally, you have the ability to carve up, as I mentioned earlier, your GPU into separate virtual components, and then map individual connections to those one by one, which is really more of a dedicated kind of thing. And a good example of that might be something like a CAD/CAM shop, where you have a number of engineers who all come in at 8 in the morning and sit down and just start cranking away. And every single one of them expects to have a minimum allocation of the GPU for his or her purposes. And so they don't want to do a lot of sharing, they don't want to be caught up in having to vie for enough GPU capabilities. Okay, optimization. I'm trying to go through this a little bit faster, but it's really fascinating. And one of the articles that I just published on the CUGC site recently was talking about, for example, things like BIOS optimization, how that can have a huge influence over the capabilities of your CPU, and that's also indirectly and directly, in some cases, over your GPU, because these two are always talking to each other. And turbo mode in particular is interesting because for a long time, Citrix actually recommended that you just run Zen servers with everything just running maximum CPU power uniformly across all the cores. And they've kind of backpedaled and changed their minds about that recently. And I've done some testing which I think corroborates that running turbo mode in many cases is actually very, very advantageous. We'll also talk about NUMA versus NUMA, the non-uniform memory access, which also makes a big difference, and multi-CPU servers, which are certainly the most common these days, I think. Their estimates that something like 80 or 85%, I think, of most servers that are sold in this day and age have 2 or more physical CPUs. We'll talk a little bit about GPU scheduling, a little bit about hyper-threading, and some of the advantages of turbo mode are illustrated in the right side here. You can see that you have a process running, and when you have enough of your cores in the low enough of an idle state, what that means is that extra frequency cycles can be delegated to those other running processes. So that instead of having a fixed frequency for all the cores, that some of your cores are allowed to run at a higher frequency. On the left here is a somewhat confusing chart, just because many vendors don't include it, do not really explain a lot of their server settings. And so you can see, for example, and this is probably the most important one, the P state, which is the power management state. A lot of those servers will come such that they are configured that the the power state management is controlled by the BIOS. And if you want to run turbo mode, you definitely do not want that setting, because I can assure you that from my own experience, it absolutely will not work, even if you have turbo mode turned on. And the reason is because if you have your Zen server installed on your hardware, the Zen server doesn't know that much about that particular button setting, so it's overlistened. Hence, you want to change it to the state where the power management is managed by the native operating system, in this case, Zen server. And once states embedded, enabled, sorry, your C states are basically the power saving states. This allows cores that are not being currently used to ramp down, so that the other cores which are executing things are able to ramp up. Here's an example of, this is a Dell R730. Here's what I ultimately ended up configuring that with after a number of struggles. You can see the turbo boost is on, C states are on, various other things are off. The uncore frequency is one of the very interesting ones. This is a really kind of a bizarre thing that took a while to research. What the uncore is basically that the core processing functions, namely, your arithmetic units, your floating point units, your main cache components, L1 and L2, are split away. The uncore functions have to do with deciding where the data flow goes. So they're all important, because this is the first step that the CPU has to process before it decides, when am I going to do these data? Okay? And they're typically, on some systems, not even one of those. Not on and off, but there are two different uncore settings. There's a dynamic and a maximum. And you think, oh, maximum is great, that's going to give me the maximum power. Well, that's not true, because very similar to running your CPU at a maximum frequency rate. For example, if I have a 2.4 gigahertz CPU, all my cores are going to run at 2.4 gigahertz no matter what, right? Well, the same thing is going to happen with the uncore component. It's going to be limited to a fixed rate. And hence, dynamic is actually what turns